Hey, hello, Integrated Science. This is Mr. B, and we are continuing with our next chapter, kind of similar to our last chapter, and then we're sticking with astronomy, whereas our last chapter was exploring the solar system. We are now going to explore the entire universe. So we're going to widen our scope of things that are existing here alongside us, with us here, rather than just staying within our solar system. We're going to see what the entire universe has to offer, but guess I could preface that a little bit. We are actually going to start with something that is in fact still in our solar system, which is the sun. But this is going to kind of introduce us to some things more about stars that again we're going to apply to outside of our solar system as well. Um, and for the sun, very important for so many reasons. Again, the big thing, it just provides energy. It gives off a tremendous amount of energy. And plants, as you can see over here in this picture on Earth, use them for photosynthesis, which again, life driving process there. Gives us oxygen. Again, photosynthesis is just a huge process. Again, that's just kind of the tip of the iceberg there. Again, in biology, next year you can get a whole chapter about photosynthesis and how that works. So, again, that's just kind of an example of what the sun does for us. So, the big thing is we just said it gives off a ton of energy, but how does the sun actually produce that energy is a huge, huge question. And to answer it, again, kind of in our key term here, we'll explain more as we go, is it's produced in the central region, so if the core of the sun, if you will, by the fusion of hydrogen nuclei into helium nuclei. So, again, nuclei just our singular term there for a nucleus, or sorry, plural term for a nucleus. We have multiple nuclei. And the reason that we are able to produce so much energy is through the process of what is called nuclear fusion, which is going to mean joining things together, which we're going to see here in a moment. So the sun gives off, again, a tremendous amount of energy in the form of electromagnetic radiation. Again, radiation is a type of energy that can travel without objects directly touching. Again, there's no object connecting us and the sun, so its rays get here through the process of radiation. And in the early 1900s, scientists discovered that the source of all of this energy comes from nuclear fusion. Again, fusion. Write that down. Nuclear fusion in its central region. In the process of fusion, less massive nuclei, so little smaller nuclei, combine together to form more massive nuclei. So little nuclei combine to form bigger nuclei. In that process, huge amounts of energy are released. Again, I can kind of explain why a little bit. I think is on this next picture here. So, how nuclear fusion works. Again, just to give you a kind of a brief overview, because it's a very complex process. So these green particles represent protons, which again positively charged particles. Purple represent neutrons. So we have hydrogen here, hydrogen here. The two hydrogens are going to combine to form helium. So again, they crash into one another. And then the reason why this releases energy is two hydrogen atoms here have more energy than these two heliums. So if nuclear fusion was not going on, if there was just hydrogen atoms floating around and helium atoms floating around, the hydrogen atoms contain more energy. So when they combine together, when these two hydrogens combine together to form helium, now all of a sudden there's less energy present here, less energy present here, so that extra energy is released in huge bursts through that process of fusion. And again, there's kind of just some of the more hydrogen forming, again, kind of kicking off those protons there, but and again, the process will keep going. So again, to give you a simple explanation, which there's really not a simple explanation for fusion, when those two things combine together, when they're separate entities, when they're all by themselves, they have more energy than when they're combined right here. So when they fuse together, they release that energy. And this process will keep going. Again, helium atoms can fuse together, and then I think it can make it all the way up to iron. So they'll keep fusing together, until it reaches a point of where it can reach iron. But most of the energy is when hydrogen combines to form helium in this process of fusion. So again, it's a much more complex process than that, but I'm just kind of giving you the abridged version there. That's all you're going to kind of really need to know for this class. So this process is again, huge amounts of energy. Again, when huge amounts of energy are present, things usually are unstable. They don't really last that long. But one thing that's really important for us, and actually extremely important for us, is that the sun is so stable. So how does the sun actually maintain this huge amount of energy but also stay stable and provide it for us over an extended period of time? Why doesn't it burn out? So the sun remains stable because the inward pull of gravity balances out the outward push of thermal pressure from nuclear fusion. So this is again a key concept, and we'll explain what that means here right now. So our fossil record, looking at it, shows that the sun has been fairly stable energy source for billions of years. Again, I think there's photosynthetic bacteria that have been fossilized that are billions of years old. Again, they were getting their energy from the sun at that point. Again, photosynthetic organisms that are alive today are still getting their energy from the sun. So these inward and outward forces within the sun must be balanced so that temperature, pressure, and density at any depth remain fairly constant over time. Again, if the forces weren't balanced out, again, the sun would push outward too much, the sun would cave in on itself. Again, it would not be a good result for life on Earth if the sun was not balanced. Again, there probably would not be. I'm not going to say probably. There would not be life on Earth if the sun was not balanced. So the energy that's created from nuclear fusion in the center of the sun causes ions, which are just positively charged particles, to move faster. So again, nuclear fusion, again, this is kind of just basic thing like there. When things have more energy, they move faster. We learned that at the beginning of the year. So the same thing happens in the sun, except on a much more great level than we could possibly imagine here on Earth, which exerts an outward thermal pressure. So again, moving fast ions exert a pressure outward. At the same time, gravity pulls the gas inward. So gravity, again, pulls everything to the center. Again, that's what gravity does. It pulls things down to the center. That's how it works here on Earth. That's how it works on the sun. So the sun will remain stable as long as there is a stable energy source within it. And again, as long as those forces are balancing out, and astronomers estimate that the sun will remain stable for another 5 billion years, which is very good news for us, very good news for other life forms on Earth. Again, 5 billion years, just a huge, huge, huge amount of time there. So again, gravity, again, just kind of a little picture here. Gravity pushes in, thermal pressure pushes out. These forces keep the sun stable and keep the sun balanced. And yep, I believe that is it for our introduction to the sun. Let me know if you have any questions.